Hi everyone, I'm Rahul Chog and I have with me Saleha Heather. We are senior solutions architects at AWS. We both have extensive experience on cloud technologies and .NET. We will be talking about how to use different AWS services for your .NET applications from architectural perspective. Welcome to the session. So as cloud has evolved over the last decade and a half, there are so many different services to deploy your .NET applications workload to. It's all too easy to find yourself in analysis paralysis mode. So in this session, we'll examine the options and simplify the decision making to help you determine the right services for your application, including container orchestrations and compute options, serverless frontends, and messaging services. We'll explore everything from an architectural lens and will navigate our way from hardware and software evolution to understanding asynchronous architectures to exploring different options to deploy to AWS services. Let's start with the hardware evolution. So the evolution has gone through several key phases, and each has significantly shaped the way software is created and deployed and the ecosystem around it. Physical servers and data center used to be the only way you could deploy and run softwares on a large scale. We made these more efficient with virtualization, but many of the same basic hardware-driven limitations remained. Moving to the cloud helped free us from the physical limitations, but we still had a lot of work to do to build and scale large software projects. With moving to virtual servers in cloud, we traded CapEx for OpEx, improved on scalability. The resources are now elastic. There is faster speed and agility. Maintenance effort has reduced. Availability is higher and fault tolerance has been better, and thus our applications have higher uptime. It has led to better automation. We are able to optimize the utilization of the resources. Provisioning speed for the resources has been faster. It's easier to set up disaster recovery now. And above all, it has imparted us with hardware independence. But we still faced issues with these virtual servers in cloud. We still need to administer them. We still need to manage their capacity and reutilization. We still need to size our workloads. We still need to manage availability and fault tolerance. And they are still expensive to run intermittent jobs. As computing evolved, containers and serverless changed the way hardware is used. It has increased hardware resource utilization, and because of that, applications now can scale efficiently. Serverless specifically has changed the way we consume hardware. With serverless, we can build and run applications without thinking about servers. There is no need to administer virtual servers or manage their capacity and utilization. There is no need to size workloads or manage its availability and fault tolerance. And with serverless, it is inexpensive to run intermittent jobs. Let's see how software architectures have changed. So this is how a typical monolithic application is designed. We have a big user interface, intertwined, highly coupled business logic, and a single data store out there. The monolithic architecture looks simple. It has many drawbacks. It's hard to scale efficiently with this architecture. So for example, let's say we have a function A and a function B, where function A needs very low CPU and memory and receives significantly higher number of requests. And function B needs a lot more CPU and memory, but receive very low number of requests. So now in this scenario, to satisfy function A's scaling requirement, one would need to scale out, but as function B is part of the same solution, you have to assign very high CPU and memory, which can take care of function B's requirement. So this This leads to inefficient scaling. Also, it's hard to iterate quickly as components are dependent on each other. A single feature would require changes in multiple dependent components. Um, each small change in any functionality requires the whole application to be built and deployed. And that makes CI/CD as well very time consuming. And because of interdependencies between modules, every change introduces regression challenges. To tackle these issues, microservices architecture came to the rescue with separate micro frontends, separate business logics, and separate data stores. With that, it increased teams' agility. Now teams are able to iterate faster and thus improve innovation as well. Now that components are totally separate, they can all scale independently based on their needs. It has also led to reduced human errors. Separating out components into microservices is not a rocket science and is very successful practice today. In fact, 10 years back, it was considered an entire pattern. So what has changed between then and now that microservices are part of the best practices now? So the answer to that question is DevOps. Now the management of these services is automated. Most enterprises have tens to thousands of microservices, and it is almost not possible to manage them without DevOps. So if you start working on any microservices focused project, start with creating DevOps pipeline for your deployment and monitoring of your services. So now let's combine both hardware and software architectures to have a holistic view. Can we deploy a monolithic application on containers or serverless? Yes, we can, but we still run into the same issues of resource utilization. As all components will have different scaling requirements deployed on the same serverless function or a container, and thus drive your cost up. But it seems with specific scaling requirements for each microservice, containers and serverless are their right home. With this, we'll be able to scale efficiently, thus keeping cost optimized based on the needs of each component being scaled. Let's dive deeper into application architecture. Here is a very standard application architecture of any monolithic app or any microservice for that matter. So client, which can be an external client or another microservice or a component of your application. So it calls the web frontend or API frontend, which further routes the request to your business logic in your backend, which in turn talks to the data store or other services to return the result. We are going to focus on this highlighted part for the rest of the session. So the front end, messaging, and the back end, and this is what we'll focus on. We'll explore architectural practices and available AWS services for your .NET application for each of those items out there. Let's have a look at asynchronous architecture and why are they important. So essentially, we'll talk about how messaging between the components should happen. To understand the importance of async architectures, we need to look at synchronous ones. Here in this scenario, let's say there is an e-commerce application, and we have a client calling the order service. Now, what if the order service fails? In that case, a client can retry after failure until it succeeds, or maybe we can have a certain number of retries out there. So it is fairly straightforward. Now, in this scenario 2, our order service further calls invoice service to generate invoice for the order. Now, what if invoice service fails? In that case, it will return error to order service, which in turn will error out for our calling client. So this leaves us with some questions. Who owns the retry? Is it the client or is it the order service? And for how long? Does the client ever know that invoice service failed? So this effectively creates a tight coupling where failures become harder to recover from. So when you start thinking asynchronously, uh, it's very different from the way you used to uh, develop applications for synchronous clients. So here on your left, you have synchronous calls. On your right, you have asynchronous. So in asynchronous scenario, service A calls service B asynchronously and does not wait for the reply from it and returns the result, while service B still executes in parallel. Going back to our scenario, order service will asynchronously call invoice service, and without waiting for the response from the invoice service, order service will return the result, while invoice service still executes in parallel to generate the invoice. So after the client can poll invoice service to get the invoice whenever it is ready at a later time. So this helped with first clearing the responsibility of retry. Secondly, as errors are not trickled to other services, you would know where errors are happening in your system. Third, the performance of the order service out here, it is affected as it is just waiting on the invoice service to complete the execution. So here, when we are doing asynchronously, it doesn't wait for invoice service to complete. So its performance has improved. And fourth, utilization. So now, as the order service does not have to sit idle while waiting for the response, so overall utilization of the service and the system has increased. So the time spent to try making a process asynchronous will pay for itself in you gaining on performance, utilization, and having a deeper understanding of what is really happening with your data as it flows through the application. So messaging services play a key role in making your architectures event-driven and thus asynchronous. We will explore different messaging services on AWS that you can use for your .NET applications. For messaging, you can use topics, streams, queues, and buses. You can use Amazon SNS, Amazon SQS, Amazon Event Bridge, and Amazon Kinesis data streams. Let's explore each of them. Amazon Simple Notification Service, Amazon SNS, is a fully managed messaging service. The PubSub functionality provides topics for higher throughput. It's push-based. Many-to-many messaging between the distributed systems is out there. It integrates well with microservices, and it's event-driven, and everything is serverless. So using Amazon SNS topics, your publisher systems can fan out messages to a number of subscriber systems, including Amazon SQS queues, AWS Lambda functions, HTTPS endpoints, and Amazon Kinesis data Firehouse for parallel processing. SQS, or Amazon Simple Queue Service, is a fully managed message queuing service that enables you to decouple and scale microservices, distributed system, and server applications. SQS eliminates the complexity and overhead associated with messaging and operating message-oriented middleware and empowers developers to focus on differentiating work. Using SQS, you can send, store, and receive messages between software components at any volume without losing messages or requiring other services to be available. SQS offers two types of message queues. Standard queues offer maximum throughput, best effort ordering, and at least once delivery. FIFO queues, which is the second type of SQS, they are designed to guarantee that messages are processed exactly once in the exact order that they are sent. Amazon Event Bridge is a serverless event bus that makes it easier to build event-driven applications at scale using events generated from your applications, integrated into your SaaS applications and AWS services. So Event Bridge delivers a stream of real-time data from different event sources to targets like AWS Lambda and other SaaS applications. You can set up routing rules to determine where to send your data to build application architectures that react in real time to your data sources with event publisher and consumer completely decoupled. With Amazon Kinesis data streams, there are no servers to manage. The on-demand mode eliminates the need to provision or manage capacity required for running applications. You can adjust your capacity to stream gigabytes per second of data with Kinesis data streams. You can get automatic provisioning and scaling with the on-demand mode. You pay only for what you use with Kinesis data streams. With the on-demand mode, you don't need to worry about over-provisioning. You can use built-in integrations with other AWS services to create analytics, serverless, and application integrated solutions on AWS quickly. So you can compare these services on these 6 areas. So first one being, you can look at your scaling requirements of the applications and corresponding concurrency control that services offers. You can look at durability offered by the service. What's the message persistence time for these services? What do the consumption models look like? How their retry mechanism work? And how much do they cost? Based on that, here is a cheat sheet for using one of these services over the other. When you have massive throughput, you need event ordering, and there are multiple consumers, and you need to replay events if required, then you should use Kinesis data streams. If you have one or minimal fan out, direct to Lambda or HTTP target, you should just use Amazon SNS. If you need to buffer requests until they can be consumed, whether ordered or not, you can use Amazon SQS. When you have one-to-many fanouts, lots of different consumer targets, you need schema matching and granular target rules, you should go with Event Bridge in that scenario. So with this, we are able to sort out our messaging aspect of the application. Next, let's have a look at web or API frontend. We are going to look at services that can be used for web or API frontend. So this is where requests from other clients, which can be external or other microservices, come to. For accessing the API frontend, we have these 3 services on AWS: Amazon API Gateway, Application Load Balancer, and AWS Async. Let's dive deeper into each of them. So Amazon API Gateway supports both REST and WebSocket protocols. With API Gateway, you have flexibility to use different authentication options. You can configure throttling per count, per region, per API, per client, alongside setting usage plans. You can implement caching as well with API Gateway. While exposing APIs to be consumed by customers for integrating in their softwares, you can generate client SDK. It also supports Open API and Swagger. So one needs to pay per request and data transfer while calling API Gateway. Then we have application load balancer. So it's a L7 load balancer, and thus can do a lot more than a standard network load balancer. So it supports SSL termination. You can route requests based on your request path. You can redirect URLs as well. You can have custom HTTP responses for your request. And if you're using containers, ALB becomes a crucial component for routing your request to containers. For ALB, you need to pay per hour and LCU consumed. Next, you have AWS AppSync. So AppSync brings GraphQL support to your APIs. Using that, you can combine data from several sources in a single response. You can polyglot to multiple different data sources. It has deep integration with Amplify framework for your web and mobile applications. You can use subscriptions for making your data sources real time, and it also supports offline sync. And for this also, you need to pay per query and data transfer when you use AppSync. Here we have a cheat sheet for picking an API fronting service. If you have a complex API with multiple data sources or have unique queries against data or offline sync, you should use AWS AppSync. If you're using WebSockets in your applications, you should use Aamzon API Gateway. If you need to transform or throttle your API request based on usage tier and you need some flexible authentication there, again, you should use Aamzon API Gateway. If you're using a regular API with potentially high number of requests per month and there is no need for added transform capabilities, then you should use application load balancer. Else, if it's a regular API with less than tens of millions of requests per month, you can fall back to Aamzon API Gateway. Another decision point is where to handle request routing. Either you can handle it in your framework or you can use one of these services as we discussed. And honestly, it's a toss-up. Customer feedback seems very split. If you love your framework, stick with it and its capability. If you want to do less work and write less code, go with the benefits of these managed services. So we have talked about messaging. We have talked about front end. Next, let's talk about the backend aspect of the architecture. So backend forms the part where you deploy your .NET code. This is where your you run your .NET application. Here we'll explore the services you can use for hosting your .NET application. But before we discuss the services, we'll talk about .NET and look at the choices we have there. So .NET has been there for over 20 years. .NET Framework 1.0 was released in 2002, and .NET Framework 4.8 is the latest version of .NET Framework and will continue to be distributed with future releases of Windows as long as it is installed on a supported version of Windows. .NET Framework 4.8 will continue to be supported. .NET Framework only runs on Windows. It is not platform agnostic. That's where .NET Core come to the rescue. .NET Core 1.0 was released in 2016, and it can run on both Windows and Linux. In the newer versions of .NET Core, the term core has been dropped, so the latest version of .NET is called .NET 6. With that, let's move onto the backend services and see where can we run our .NET applications. So EC2, Lambdas, and containers provide the compute, that is CPU and memory, for your .NET applications. Let's dive deeper into each of these, and we'll view it from the lens of running older .NET Framework applications versus running newer .NET Core applications as well. So EC2 service provides virtual machines on AWS. EC2 provides secure and resizable compute to support any workload. You can optimize performance and cost with flexible options like AWS Graviton-based instances, Amazon EC2 Spot instances, and AWS saving plans. To automatically manage scaling in and scaling out of EC2 machines, you can use auto-scaling groups, which can scale EC2 based on metrics like CPU usage, memory usage, and many more. If you want to run your older .NET Framework applications on EC2, you need to run Windows operating system on them. This is significantly costlier as Windows licenses add to the running cost. On the other hand, if you're running .NET Core, it can run on both Windows and Linux. With .NET Core, you can also leverage gain in performance for Graviton-based instances when using .NET 5 and above. Lambdas form the heart of serverless computing on AWS. Lambdas being serverless requires no administration and scales automatically based on usage. You can deploy your .NET Core on Lambdas as functions aligned to an event source from many different AWS services. So they serve as a perfect use case for one-off task execution based on certain event. You can use AWS step functions to manage the workflows for interacting with multiple microservices and multiple Lambda functions out there. Lambdas have a Linux-based OS, and thus older .NET framework cannot run on Lambdas. You can only run .NET Core code on Lambdas. So containers, they are the lightweight, standalone executable package that includes all dependencies, your code, your runtime, system tools, system libraries, and settings. They isolate software from its surroundings. This eases deploying code on different environments, dev, test, staging, and production. And also it reduces the conflicts between teams running different softwares on different infrastructure. So from .NET perspective, if you're using .NET Framework, you can use Windows Server Core or full Windows Server images for your application. If you're using .NET Core, you can use Linux images, or you can use Windows Nano Server image. So these images are very light and have faster boot time. So that being said, .NET Core is more suited for container applications. But if you have applications that are using older .NET Framework, you have to use those heavier containers. Just want to mention here another route here. You can port your application from .NET Framework to .NET Core. Though this can be a huge effort. We do have a tool called Porting Assistant for .NET, and it can help with significantly reducing this modernization effort. For managing orchestrations of these containers, we'll talk about orchestration options in the next section as we dive deep on containers. So moving on to this cheat sheet for picking the right backend service, if you have monolithic application, which has OS dependencies like Windows Registry or have any third-party software dependencies that can only be installed on a VM, then you have no choice but to use EC2 for serverless functions, for or intermittent short tasks, and if you have .NET Core, then you can use Lambdas, and you can use step functions for simple workflow management there with Lambdas. If your application requires complex orchestration with no hard dependencies on the OS services that are not available to containers, and you want granular control on compute scaling, or if you have long running tasks out there, you should use containers for that. So we have filled our architecture diagram with backend services options as well, but we should further deep dive on container options on AWS. So I'll hand over the control to Saleha to complete the understanding on container options.
Thanks, Rahul. Let's talk about containers on AWS. The current AWS container services landscape covers a broad set of products grouped into image registry, orchestration, and compute. Let's look into each of these. For image registry, we provide a registry service, Aamzon Elastic Container Registry, where you can store your container images privately or publicly. At the management layer, we have Aamzon Elastic Container Service, ECS, Aamzon Elastic Kubernetes Service, EKS, Red Hat OpenShift on AWS, also called ROSA, and AppRunner. EKS makes it easy to deploy, manage, and scale containerized applications using Kubernetes on AWS. You can currently run your containers on ECS using either the EC2 launch type, where you get to manage the underlying instances on which your containers are running, or you can choose to run your containers in a serverless manner with the AWS Fargate launch type. With App Runner, you can forget about managing auto-scaling, load balancer, and even CI/CD, and just focus on your application code. Rosa allows you to transfer your OpenShift skills from the on-prem environments. For compute, we have EC2 and AWS Fargate as options. Now, let's take a look further at each of these products in a bit more detail. So, Amazon Elastic Container Registry, ECR, is a fully managed container registry that makes it simpler and faster for developers to store, manage, and deploy container images. It is tightly integrated with AWS Container Services and other AWS services such as CloudTrail, Audit Logs, and IAM. It is backed by Amazon S3 with regional endpoints and cross-region replication. On Amazon ECR, you can store container images, push updates, pull from it, and so on. It provides the same fundamental function as a service like Docker Hub, but it's private and integrated with our managed container services that I will introduce shortly. Amazon Elastic Container Registry Public, ECR Public in other words, allows you to store, manage, share, and deploy container images for anyone to discover and download globally. With Amazon Elastic Container Registry, you have long been able to host private container images on AWS, and with ECR Public, you can host public ones too, enabling anyone to browse and pull your published container artifacts. The Amazon ECR Public Gallery is a public website where you can discover and download container images globally. The choice of orchestrator is important, as this is the key integration point. It will deeply influence the rest of the choices you make. One of the most common requests we hear from customers is, help me decide which container service to use. We recommend that most teams begin by selecting a container solution with the attributes most aligned to their application requirements or operational preferences. We have our ECS container service, which is powerfully simple, easy to use, and natively integrates with other AWS services. We have EKS, which is openly flexible. If it runs on Kubernetes, it runs on EKS. It is great for customers who are already consuming Kubernetes and are looking to continue that in a managed fashion on AWS. Then we also have ROSA, Red Hat OpenShift on AWS. This is really our turnkey container platform, meaning that everything that you need to run a container platform backed by Kubernetes is available through ROSA, from your CI/CD to your observability. Let's dive into each of these. Amazon Elastic Container Service, ECS, is a fully managed container orchestration service. What customers tell us they love most about Amazon ECS is the simplicity it provides. Amazon ECS delivers an AWS opinionated solution for running containers at scale. It reduces the time it takes customers to build, deploy, and migrate their containerized applications successfully. Amazon ECS powers a growing number of popular AWS services trusted by hundreds of thousands of customers. Customers adopting containers at scale seeking powerful simplicity should start with Amazon ECS. Now, Amazon Elastic Kubernetes Service, or Amazon EKS, is a managed service that you can use to run Kubernetes on AWS without needing to install, operate, and maintain your own Kubernetes control plane or nodes. Teams choose Kubernetes for its vibrant ecosystem and community. consistent open source APIs, and broad flexibility. They rely on Amazon EKS to handle the undifferentiated heavy lifting of security and operating Kubernetes at scale. EKS is optimized for customers building highly available shared services platforms based on open source. Now, Red Hat OpenShift Service on AWS, or ROSA as it's called, makes it easier for you to focus on deploying applications and accelerating innovation by moving the cluster lifecycle management to Red Hat and AWS. With ROSA, you can run containerized applications with your existing OpenShift workflows and reduce the complexity of management. Most customers choose to run OpenShift on AWS because they want to keep existing tools and practices while leveraging investments in the vast AWS services portfolio. So, ECS, EKS, and ROSA support a broad array of compute options. They also have deep integration with other AWS services and provide the global scale and reliability. ECS provides powerful simplicity. It's an AWS opinionated way to run containers at scale. It allows you to reduce decisions without sacrificing scale or features. Also, it allows you to reduce time to build, deploy, and migrate applications. EKS provides open flexibility. It helps you run Kubernetes on AWS without installing, operating, or maintaining your own Kubernetes control plane. Red Hat OpenShift Service for AWS ROSA provides an integrated experience to use OpenShift. If you are already familiar with OpenShift, you can accelerate your application development process by leveraging familiar OpenShift APIs and tools for deployment on AWS. Let's talk about serverless containers. AWS Fargate is a serverless compute engine for containers that works with Amazon ECS as well as Amazon EKS. Fargate takes the toil away from managing your own compute infrastructure. There are no instance types to select, virtual machines to monitor, and no operating systems to patch. Your application gets the CPU and memory you ask for, and you only pay for those resources. Thus, Fargate makes it easy for you to focus on building your applications. Let's go one step deeper. Fargate is a fully managed compute platform. It changes the shared responsibility model compared to traditional EC2 instances. Starting from the bottom here, Fargate provisions a virtual machine for each of your tasks or pods. It always provisions the most up-to-date operating system, and Fargate takes care of the software updates. The container runtime is also fully managed by Fargate. Fargate manages ephemeral storage for your task and encrypts the data by default. And finally, Fargate has out-of-the-box integration with CloudWatch logs, container insights. What you are left with is only thinking about building your application. Fargate manages more and you spend less time on infrastructure setup and operations. Serverless is more than compute. While many customers associate serverless with Lambda, there are actually serverless services at all layers of the stack. AWS Lambda supports container images as a deployment model. And while Lambda offers many key advantages for our customers, it's really when all of these components like messaging, orchestration, storage, and compute surround Lambda that we start to see much bigger benefits. So our customers want to invest in a set of tooling for the first part of your software lifecycle, the edit, the build, the test, and package phases. Which is why we launched the ability to define and package Lambda functions using container images. Our goal here is very simple: We want customers to get the full benefit of their investment in container tooling for building and packaging software, while also getting the full benefit of Lambda's native service integrations, simple programming model, and pay-per-use billing, and built-in automated scaling that is more than an order of magnitude faster than cold start scaling in container orchestration systems. App Runner. App Runner is the easiest and fastest way to build, deploy, and run modern containerized web apps and APIs on AWS. It doesn't require developers to have any previous containers or infrastructure experience. And it's built on top of Fargate, the serverless compute engine that powers hundreds of millions of containers on AWS. App Runner also ensures consistent application and API response times by reducing latency and eliminating cold starts. App Runner is built for web scale. This means that startups starting out on App Runner don't need to re-platform their apps as their business grows. With App Runner, rather than worrying about re-architecting their apps or configuring infrastructures, developers can focus on their code and benefit from the portability, efficiency, and cost savings of containers. That brings us to the summary. I'll hand it back to Rahul to take you through it.
Thank you, Saleha. So this completes our today's session. We talked about hardware and software evolution to serverless and containers. We talked about the importance of microservices and async architectures. We discussed in detail the options available for front-end, messaging, and backend services on AWS for your .NET applications. I hope the session was helpful, and we are looking forward to your feedback. Thank you, everyone, for attending today's session. You can connect with us on Twitter or LinkedIn. Our handles are on the slide.